Basic Calculus 6, Graph Sketching, Part 2 of 4. We'll start with an example, then there'll be a whole lot for you to try. So we have the f of x equals x plus 2 times x minus 1 all squared. AN is perpendicular to the y-axis, which means it's a horizontal line, and immediately you should realize that means it's going to have the equation y equals a constant. Notice that the square bracket, there's just a little hint to keep in mind. The square bracket means that there are two x-intercepts the same, so they've come together, so there has to be a turning point at 1. So I know that's the point x value of 1. So I'm going to multiply out. Square that out first, then I'm going to multiply those, because I need to differentiate in order to find the coordinates of the turning point. Derivative equal to 0. Divide through by 3. Solve for x. We need the turning point's coordinates, so I'm going to now substitute those x values back into the original. And we pair them off. Part 2. OB. Find the length of OB. Well, it's the difference between the x values of 1 and 0. Part 3. The gradient of the curve at x equals negative 2. The gradient of a curve is the derivative, or the derivative is the gradient. Derivative is the rate of change, and the gradient is the rate of change. So I'm going to substitute negative 2 into the derivative. And the gradient is 9. The equation of the line AN, you already spoken about that. Y equals 4, horizontal line, y equals a constant, and it goes through the point negative 1, 4. C, the point at which with F cuts AN. Well, that means f of x must equal 4. Point of intersection of y equals f of x, so y equals 4. Now we'll need to factorize that. There are two ways to do it. Well, three ways. You could use factor theorem to find the first factor, then division by inspection, or factor theorem, then long division, or you could use a little bit of knowledge on the sidelines. This line touches the curve. So therefore, in a way, those are equal solutions there. Negative 1 is an equal solution for this line cutting the curve. Instead of cutting 1, 2, 3 places, it only cuts at 2 places, because these two values have come together as this line goes up, and they become 1. So there are two values of minus 1, which means we'll have x plus 1 squared. Now x squared times x gives you x cubed. 1 squared, which is 1, times minus 2 gives you minus 2. That's how I determine what that is, by saying, well, what are the end values of this one? And we get x equal to 2, being the x value of that point. And there the coordinates of point C. We know the x value is 2, we just found. It lies on the line y equals 4, so the y value is 4. AN and AC. AN and AC, well, difference between the x values, this being a horizontal line, and difference between the x values. Here are some exercises for you to do. There are 2 screens of it. Pause, do them yourself. If you need to look at the solutions later on, then try them again yourselves and then go through the solutions again. If you're going to become good at the maths, you must make sure that you complete examples on your own in the end. Number 1. F of x equals x cubed minus 12x squared plus 36x. Coordinates to the turning points of A and B. Turning points A and B. Derivative equals 0. Solve. I'm going to divide through by 3 first, just to simplify the factorizing. So we have the x values. We need to substitute back into the original to find the y values. So we now have the turning points. Find the length of OB, well, distance of the x value of 0 to the x value of 6. Gradient of the curve at the origin. The gradient of a curve is given by the derivative, the rate of change. So therefore the rate of change when x is 0, we're going to substitute 0 into the derivative. F prime 0. 36 is the gradient. Equation of the line AN. Well, it's a horizontal line, which means y equals a constant. It's going through the point 232. Therefore, y equals 32. See, the point at which y equals f of x cuts AN. So there's y equals f of x, there's AN. So we need to know that point there. So therefore we must have f of x equal to 32. You solve the equation. Our heart sinks. Is this another factor theorem? This is another one of these cases where AN touches the curve there. So instead of cutting 1, 2, 3 places, it's cutting at 2 places. So these two, as the line gets higher, have become 1. So there are 2 x values of 2 there in effect. 2, 2. Which means 2 brackets, x minus 2, x minus 2, giving you x minus 2 squared. So therefore I know that that has to be a factor of that equation. Now to get the x value, we just say, well, x squared must multiply this to give you that x cubed. Minus 32 at the other end. This end value must multiply that end value to give you minus 32. So it's x minus 8. Question says find the coordinates of C. Well, we know the x value now is 8, and it's on the line y equals 32. AN and AC, difference between the x values. Question 2. F of x equals 2x cubed minus 3x squared minus 36x plus 37. Use factor theorem to find one linear factor of f of x. So that's trial and error. And when we tried 1, it worked. If you're doing this in an examination, then don't show all your substitutions. Do them in rough and only show your substitution that works in the examination. There are not going to be any marks for showing all the other substitutions there. Who knows, you may have only had one. The graph of f with x-intercept at B and y-intercept at A is shown. Find OA, which is distance between the origin and the y-intercept, and OB, distance between O, the x values O and the x value B. So A is 37. That's pretty straightforward to find the y-intercept there. OB is also straightforward because we've already found the first factor, 1. Now we're going to find the coordinates of the turning point. Derivative equal to 0. I'm going to divide through by 6 to simplify. Factorizing, we get 2x values. We have to find the coordinates, so we substitute into the original to get the y values. And there are our turning points, our stationary points. Tangent to the curve at Q cuts the curve again at T, so that must be T there. Find the coordinates of T. Have we seen this one before? Aha. Common question, hey? That equals minus 44. Now, as in question 1b, part 2, we don't have to use a whole big substitution, to find factor, use factor theorem, because we know it touches at x equals 3. So therefore I now have x minus 3 all squared. Now when I square out, I get x squared, and I need a 2x cubed, so that must be 2x. When I square out, I get a plus 9 at the end. I need 81, so that must be a plus 9. Therefore, my x value at this point is negative 9 over 2. And that's very quick because it's the y value of negative 44. It's along that line. The gradient of the curve at B. Right, so at B, x is 1, so I'm going to substitute into the gradient, into the derivative. Values of t, will the equation that equals t have two distinct roots? Only one root, no real root. So we're going to have a sideshow. Let's go into this with the different roots. There's f of x equals g of x. So there are three distinct roots. You see it cutting there, there, there. So a, b, and c are the roots. There's a graph only cutting in two places. This is steeper than this, so this won't meet. So therefore, we have two solutions, there and there. This one also cuts in two distinct places. Touches there and then cuts again there. Won't cut further. And this only has one real root or solution. If I have f of x equals g of x, it only cuts there. It's not going to cut anywhere else. So if we go back to the equation here, values of t, will the equation that equals t have two distinct roots? Well, we know that's this graph. Y equals t will be a horizontal line, so it says where will the horizontal line have two distinct roots? Well, either there below or there above. This is one with none, sorry. First, there's g of x, there's f of x. You'll notice they don't cut at all, so that is no real solutions or zeros. Do not cut. I don't know who spelled that. So now look at intersection of those graphs. There's y equals t. Any horizontal line drawn. So let's go again. You see it can move anywhere because it's y equals t. Now, two distinct routes, which means there and there. Those are the only two places. Therefore, t is 81 or t is negative 44 for the line y equals 81 or y equals negative 44. Only one real root. Well, there. Let's show again. Only above there or below there. Which means that we have t greater than 81 or t less than negative 44. No real roots. Well, where can we draw a horizontal line not to cut this graph? Nowhere, because this is going down forever, that's going up forever. A horizontal line will always cut it at least once. No values of t. Number 3. F of x equals x cubed minus 3x plus 3. Find f prime of x and hence determine when it's equal to 0. So there are f prime x equal to 0 plus or minus 1. Turning points of the graph of f. Well, we know the x values. Substitute the original and we get the y values. There are y values. There are turning points. Points of the graph which the gradient will be equal to 9. Will be 9. Well, gradient will be 9 means derivative will be 9. Yeah, derivative equal to 9. There's derivative. Put it equal to 9. Solve for x. Plus or minus 2. Now we need to substitute back to get the y values. And there are our points. F of minus 2, f of minus 3. There's f of minus 2. There's f of minus 3. Now note the one's positive, the one's negative. What can you conclude about at least one root of the equation f of x equals 0? Well, this is all to do with this here. If you have a look, there's minus 3, minus 15. There's minus 2, 1. Do you notice this graph has to cut between minus 2 and minus 3? What can you conclude about at least one root of that equation equals 0? Oh, we've done that. Find the equation of the tangent to curves at its turning points. Well, at the turning points of a curve, the line is horizontal. Therefore, it's y equals the y value of the turning point there. And the xy equals the other y value of the turning point. Points at which these tangents again cut the curve. Well, we have f of x equals 1, f of x equals 5. So we need to know that point there and the other point. Once again, it's touching, so we have an x plus 1 squared there, x minus 1 squared there. Therefore, x minus 1 squared, because of the touching at x equals 1. X minus 1 squared, because it's touching at x plus 1 squared, because it's touching at x equal to minus 1. And there are our two values. Minus 2 and the x value of 1. 2 and the x value of 5. Remember how we got that? We say, well, these multiplying out must give us x cubed minus 3x plus 2. This is x squared, that must be x. This is plus 1, this must be plus 2. This will have an x squared at the beginning, therefore it must have an x to give us x cubed. To get a minus 2 there, this will have a plus 1 at the end, therefore there must be a minus 2 to give you minus 2. Number 4. f of x equals 8x cubed minus 24x plus 9. Find f prime x and hence determine. Well, there's f prime x. Determine the turning points of the graph. I put it equal to 0. Divide through by 24. Notice we've got a common factor of 24, so that we can divide through because it's equal to 0. Solving for x. Substitute to get the y values, and there are turning points. Points of the graph which f prime of x equals 30. So we take f prime of x, put it equal to 30, and we solve. Those are the x values. Substitute to get the y values, and there we have the points. Notice there we are. Plus 3 over 2, 0, minus 3 over 2, 18. What do you know about the graph of f at these latter points? Well, f prime of x equals 30, which means the tangents to the curve at those points will be parallel and their gradient will be 30. Find f of that, f of that, f of that. What information do these values give you about the zeros of f? Well, that means 3 over 2 is a 0. F of minus 1 is 25. F of minus 2 is minus 7, which means that there must be a 0 between those two values. Eh? Find where the equation of the tangent at x equals 1. So we're going to find the gradient by substituting 1 into the derivative. And we need to substitute 1 into the original to find a point. So 1 into the derivative, and we have a point. So there we are. Notice when we substitute 1 into the derivative, we get 0, which means m is 0. Which means y equals mx plus c will end up with y equals negative 7. Find where this tangent again cuts the graph. Have you seen this question before? Notice x minus 1 all squared. Again, because it touches there. It's a straight line, horizontal. Therefore, we can find the x values there. Minus 2, minus 7. Minus 2 because of that. Minus 7, well, it's on the line y equals minus 7. Find f prime prime of x. There we are. So we differentiated the derivative. Determine on which intervals the graph is concave up and down. Well, remember, for concave up means happy, positive, which means second derivative positive, and concave down, second derivative negative. So it's less than 0 when x is less than 0, which means concave down for x less than 0, concave up for x greater than 0. Any points of inflection on the curve? Well, points of inflection occur when the second derivative equals 0. And therefore x equals 0 is a point of inflection.